Imagine copying a 3 billion-letter manual by hand in hours without a single mistake. This monumental task requires a microscopic construction crew working on your DNA. If this crew started at one end of the strand and worked their way to the other, the project would take weeks to finish. To finish quickly, the crew breaks ground at thousands of specialized starting sites all at once. These sites are strategically chosen, rich in chemical pairings sharing only 2 bonds, rather than 3. These weaker links are the easiest places to pry apart. By finding the path of least chemical resistance, the cell ensures this massive project launches with maximum efficiency. As the crew opens the site, the DNA unzips into a Y-shaped active zone where the actual building happens. The unzipper tool drives through the center of the double helix, splitting the strands to create the workspace. This forceful prying creates massive twisting tension. To prevent knotting, an untangler tool moves ahead, temporarily snipping the strand to relieve pressure before seamlessly rejoining it. Once the strands are separated, they are fragile and want to snap back together. To prevent this, protective scaffolding proteins instantly clamp onto the exposed single strands to hold them steady and keep the site open. Without this coordinated prep crew, the DNA templates would immediately tangle or slam shut, making it impossible for the builders to do their work. Now that the site is open, the builders can move in. However, the main building enzyme cannot start a new strand from scratch. It needs a pre-existing foundation to lock onto. A foundation layer tool solves this by dropping a short starting block onto the exposed DNA. The master builder then locks onto this foundation, sliding forward rapidly to leave a perfectly matched new strand in its wake. This side of the site is the continuous strand. Here, the builder follows right behind the unzipper, copying the code in one unbroken motion. This smooth, forward-moving workflow is the cellular assembly line at its absolute best, fast, efficient, and perfectly steady. But the other side of the site presents a logistical problem. The builders can only move in one direction, and on this strand, that direction points away from the opening split. To handle this backward strand, the builder works in leaps. It waits for the unzipper to open a new section, attaches near the split, builds a short segment moving backward, then detaches and jumps back. This stop-and-start method leaves behind a trail of disconnected chunks of DNA. To finish the job, a specialized glue tool glides over these fragments, physically sealing the gaps to create one continuous strand. Even with these strict directional limits, the crew finds a way to ensure both sides of the instruction manual are copied perfectly. Accuracy is everything here. A single typo out of billions of letters can cause a genetic mutation that prevents a cell from ever functioning again. The first line of defense is built into the chemistry itself. The physical geometry and chemical properties of the genetic letters act as natural matches. An incorrect match simply won't fit into the space, naturally rejecting most errors before they happen. The second defense is proofreading. The builder instantly checks each letter. If incorrect, it reverses to backspace the error, replacing it with the right piece. Finally, an inspection crew scans the finished DNA, cutting out lingering structural flaws and patching them with perfect code. This tireless crew unzips, builds, and triple-checks billions of letters with near-perfect accuracy. Ultimately, this continuous construction project is the reason your body can grow, heal, and survive every single day.